Hi everyone. Thank you for the introduction. It's been a pleasure for me to be here and talk about the work we have recently published in CGO25. As the title suggests, in this work we leverage the sparsity available in quantum simulations, and we focus on using an intermediate language to develop a compiler to generate an optimized quantum simulator. More specifically, we focus on the quantum gates, and we take the high-level linear algebra behind the quantum simulation for each quantum gate, and we try to translate this high-level linear algebra to optimize low-level code. Throughout this talk, I will briefly go over the basics of quantum simulation and show how these simulations can be done by highly structured and sparse matrix vector multiplications. Then I will show how we can improve the performance of these simulations by capturing this structure and sparsity in the matrices. And I will speak about the required optimizations, and I will show that how hard it could be if we want to handle these optimizations manually. At the end, I will present our approach to address these issues, which is, as I mentioned, using an intermediate language to translate the high-level linear algebra to an optimized low-level code. And at the end, I will wrap up the talk with some of the results that demonstrate the improvements our approach had in terms of performance, maintainability, and extensibility. Let's talk about quantum computing and quantum simulation. Quantum computing, as you may already know, is a very hot topic because quantum computers can handle problems including high amount of information, and they can process them much easier and faster than classical computers, where classical computers are even either too slow or even unable to handle the problem. It has use in several areas like cryptography, optimization, machine learning, material science, and chemical reactions. On the other hand, we have quantum simulations. Why it's important? Because it's acting as a bridge between quantum computing and classical computing. At the moment, quantum computers are in developing stage. They are not fully developed. They are limited in the number of physical available qubits. They are very noisy, so even most of these available qubits are used to correct the noise available in these systems. So we can, at this stage, we can use quantum simulation to test the quantum approach, the quantum algorithms, validate them, use as a training tools for people, because the quantum computers, even the available ones, are not easily approachable by everyone, but the personal computer is more accessible and we can do the quantum simulation. What are the differences between quantum and classical computing? Similar to classical computing, we need to store data in quantum computing. But instead of a classical bit, which can be represented by a scalar value and can store a 0 or 1 value, In quantum computing, we deal with quantum bits or qubits for short. Here, qubits can be presented by vectors instead of scalars. For example, these are the state vectors, the zero state vector on the left and one state vector on the right. One important feature in quantum computing is that not only a qubit can have a 0 or 1 value, it can have both values at the same time, which is called superposition. If we have more than one qubit in our system, we simply can do the conical product of their state vector to achieve the state vector of the overall system. For example, at the bottom, we can see the state vector of a 2-qubit circuit where the first qubit is in state 0 and the second qubit is in state 1. In order to modify the state of a qubit, we need some operators, which is called quantum gates, and can simply be represented by complex matrices. To calculate the output state of a qubit after the application of the quantum gate, we simply multiply the matrix of that quantum gate to the initial state vector to calculate the output. This is very straightforward and simple algebra. We can use any tools we prefer to implement such a calculation. For example, we can use NumPy. But in real-world circuits where we have several qubits, this problem is far more challenging. Not only the simulation times increases exponentially by adding new qubits to the system, we cannot even go further than few qubits using this simple approach in a normal personal computer because of the memory limitations we have. But this is not the end of the world. We have specific tools to address these problems. For example, we have simulators like Quest, which can easily handle such problems, and we can use several qubits in the circuits to simulate the circuit. To understand how these specialized tools work, let's have a closer look to the linear algebra behind this quantum simulation. Consider a 3-qubit circuit, a very simple circuit with 3 qubits here, which we only have 1 qubit, a single qubit in this case, applied to the second qubit. The other 2 qubits should retain their initial state vector because no gates are applied on them. This is equivalent to having identity matrices applied to them or identity gates. In order to compute the output state vector of this system, we need to construct a bigger matrix here, which we call overall transformation matrix, or OTM for short. The algebra again is simple. We simply do the conical product over the matrix applied to each qubit to calculate the OTM, and then multiply the OTM with the initial state vector. For example, in this case, if we assume the primary gate is a Hadamard gate, this on the right-hand side, we can see the overall transformation matrix we can construct for this circuit. In general, for an n-qubit system, we are looking at a complex matrix of size 2 to the power of n by 2 to the power of n. And this is where we have the issue of using general tools like NumPy here. But if we look at the OTM metrics, we can see that, okay, it's highly sparse, and even more importantly, the sparsity has nice structure, which is dominated by the conical product of the identity matrices on the left and on the right hand side. Each of these matrices repeat the values of the primary matrix in different ways. Okay, so far we have a sparse matrix, and we want to multiply it with a vector, which I can say it's normally dense in most of the quantum simulations, and we can use sparse tools to handle this. We can overcome the memory limitations, but it wouldn't have the best performance because we still rely on the size of the matrix or the vector. But the way the specialized tools like Quest handle these problems is that they do not even construct the OTM matrix at all. Here, they calculate some indexes, which are the indexes of the elements on the state vector which we need to update at each iteration. And they use those indices to directly modify those elements in the state vector without constructing the OTM matrices. And this is how we can achieve such a good performance in these specialized tools. But there is another side to be considered here, which is the maintainability side of the problem and the solution. What I have showed in this slide and the previous slide is a sample function implemented by the Quest to simulate the Hadamard gate in this example. This is for the CPU version of their implementations. They have implemented similar functions for the remaining quantum gates, like C0 gate and etc., swap gates, etc., etc. But they have a limitation, so they have limited only to the commonly used quantum gates, and they have some generic implementations to implement the remaining quantum gates if somebody needs. But as I said, this is only for the CPU version. They have implemented similar functions for the GPU version. So this approach, although has a very, very good performance, it suffers from the maintainability issues. If they want to support a new backend, they have to re-implement all the functions or the similar ones for the new backend. If they want to add a new optimization, if they want to change the data layout, they have to manually do all the things from scratch. So, what other approaches are possible? As mentioned, Quest has a very good performance, but it has maintainability issues. On the other hand, we have other specific tools like Qiskit, which, due to the huge community behind it, has a better maintainability compared to the Quest. Or we have approaches like Catalyst from Pennylane, which they have used compilers and intermediate language to support the new backends much easier than what has happened in Quest. But first, they don't have the best performance, such as Quest. Second, they still rely on manual implementations of quantum gates in their low-level code. To address this, we have introduced LFQS, which combines both features, both the performance and maintainability here. The high-level idea of LFQS is to take the linear algebra, translate it to optimized low-level code. How we can do this? We have implemented a two-stage approach for this. As I said, we are using an intermediate language, in our case, STQL. We translate the linear algebra to the STQL and feed it to our compiler as the naive representation of this algebra. Our compiler, through several optimization stages, optimize this naive expression. And at the end, the optimized expression is fed to the code generator, which generates which translates this expression from the intermediate language to the desired backend. Currently, we are supporting both CPU and GPU versions. For the CPU, we generate parallel C code, and for the GPU version as well. First stage, as I said, is the compiler version. This is the unoptimized or naive expression. Each of these green keywords are corresponded to several lines of code. And as we can see, there are several intermediate matrices. As I said, we can remove these intermediate matrices to overcome the memory limitations. On the other hand, it has several steps of calculations which can be merged together to improve the performance. The goal is to achieve an optimized expression like this, which is then fed to the second pass, which is our code generator. As mentioned, for the CPU version, we are producing parallel C code. Each of the expressions in STQL have an equivalent structure in C. For example, let bindings are translated to variable definitions, or some expressions are translated to for loops. And at the side, we are generating required syntax or commands for the parallel execution as well. One of the strengths of our approach is that if we want to handle a new backend, we can still use the optimized expression shown on the left-hand side and just do the new code generation. For example, this is the GPU version generated from the same expression. Now I'm going through the performance, and I guess I'm running out of time here. This is the performance for the CPU version, which we have compared the performance over several real quantum circuits with 26 qubits in each circuit. The closest competitor is Quest, which we outperform it by approximately 3.5 times being faster. For the GPU version, again, we are faster than Quest, almost 1.6 times faster. On the maintainability side, we have considered several scenarios. Adding a new quantum gate to the circuit, Quest requires roughly 40 to 50 lines of code to be implemented for a new quantum gate, but we do handle it with just one line of code where we define the gate matrix. Changing the data layout, again, for the available gates in Quest, they need to modify around 130 lines of code, which we handle with 5 lines of code. For supporting a new backend, they have implemented more than 500 lines of code, which we handled with 90 lines of code. And yeah, if you need more information, you can go to the paper with more detail on the implementation.